we've already gone through the Bayes theorem in the form of events and in the form of parameters and data. Now we are going to add some complexity. We are going to add the idea of models. So first, let's start with this version of the Bayes theorem. Now, this looks like the parameters data form, but you see here that you've got an H1 there, an H1 there, an H1 there, and H1 there. What's this H1? Well, this is a model. In this case, we call it H1 because it's the model of the alternative hypothesis. It doesn't need to be the model of a hypothesis. It can be a different type of model. But in this case, we're going to use it as the model of the alternative hypothesis because we want to use this in order to compare these to a model of the null hypothesis. Okay? So now, if you notice something, we've got H1, but this doesn't change anything. Why? Well, because there is no probability associated to H1, and we assume that H1 is true. That means that the probability of H1 being true is 1. So, if we are not associating any probability, we don't have to worry about that. We have to do the calculations as we did before. If we had times probability of H1, then it would be different. We need to care about what's the probability of H1. But with this format, we don't have to worry about the probability of H1, so it will be equivalent to what we've done before. So why do I add this H1? Well, because I'm going to compare this model with this model. And this one is the model of H0. And what does it have different apart from having these H0s there? Well, the prior distribution in this model will be different than in this one. We are going to keep the same likelihood, but we are going to vary the prior distribution. And then we are going to compare the two models. So if we follow the same procedure as before, I'm going to do it very quickly this time because I went through this before. We use the grids here that I've already prepared. We've got the prior distribution here. This is a normal distribution. I'm putting the more higher probability in the center, and as you go away from the center is less probability. Then this is the probability of the data given the parameter value. So if we are considering this parameter value, the center of theta, well, the probability of the data, which is data is here, it goes lower as it goes away from that value, that central value. And that would be the same if we consider this value. This is the distribution, this value, this is the distribution, and so on and so forth. But of course, I'm putting a finite number of distributions there, but in fact, these are infinite number of distributions, so it is technically not correct what I'm showing. And then we are going to do the prior times the likelihood, and then we've got the numerator of the theorem, and we've got something similar to what we got in the previous videos. Now, what about this model? This model, we are going to see it there, and the prior is absolutely different. In this model, we say that the whole probability is in 0, so theta equals 0. and we've got a model for the likelihood is the same as in here. Why is the same? Well, if this is the value of theta, then the data, probability of the data, is given by this normal distribution in which the values at the mean are the highest probability. You go further away from the mean and you've got lower probability. The only difference with the other model is that we only have to do this for the value of theta equals 0, because the prior told us that all the other values are impossible. We give them a probability of 0. Okay, so when we do this times this will be exactly the same. We don't, no change, because we don't have probability for other values. So we've got this difference, the difference between these models, these values in the numerator of the Bayes theorem and versus this in the other model. And then we've got, if we add, let's say the data is here, so the sum of these values or the integration of these values will be the probability of the data for model H1, and this value, I don't have to add anything because it's just one possible value there. We reproduce that here. So we got these two values of probability of the data for the different models. In this case, I'm not going to worry about the posterior distribution, because with this, with the probability of the data, that's all I need to do the Bayes factor, which I will explain in a minute. Now, I need to do something else. I need to do another theorem, another Bayes theorem, but in this case, it will be about the model. So remember the general form of the Bayes theorem. The general form is about events. So anything could be an event. It could be the hypothesis that something will happen, and I can use a model to represent that hypothesis. So if I can apply the Bayes theorem to any event, then I can apply it to a model, isn't it? Yes, of course I can do that. Now, so I'm going to write down a Bayes theorem, but we want to know what's the probability of the model of the alternative hypothesis after observing the data. Okay, so I'll do it here. Probability of model of the alternative hypothesis given that I observed data. That's the same as the probability of the data given the model of the alternative hypothesis. And that's multiplied by the prior I give to the model of the alternative hypothesis. So we had the H1 there, but now we've got H1 with some probability associated with it. So that changes things. So now I have to divide by the probability of the data. And I'm going to do the same, but for the null hypothesis. So I'll do probability of the model of the null hypothesis given the data equals the probability of the data given the null hypothesis times the prior distribution for the null hypothesis, and that divided by the probability of the data. Now, this probability of the data and this probability of the data is the same. That's probability of the data regardless of the model. So it's like making an average of the two models, some sort of average of the two models, and determining what's the probability of the data as an average of these two models. But because that's the same value, I can cancel and ignore it. So if we do that, then the way I can compare these two models is by using ratios. So let's put that in a different form of the Bayes theorem, which is the use of odds. Okay, so we are going to use odds. Now, we have one component of this odds version of the Bayes theorem is probability of H1 given the data over probability of H0 given the data, and that's the posterior distribution of the model, so we call it posterior odds. And that's equal to the probability of the data given H1, which comes from here, divided by the probability of the data given H0. And that we call the Bayes factor. But that doesn't finish there. I have to multiply the Bayes factor times the priors for the models. So probability of H1 over the probability of H0. So we've got now, and this is the prior odds. These are the odds we give to the models before we observe the data. Now, what we have now is the way that something we can use to compare these two models. Now, if we decide to give the same probability to H1 and to H0, so 50% chance of H1 being true and 50% chance of H0 being true, then that cancels. So that means that if we cancel these, then the posterior odds equals to the Bayes factor. So we don't have to worry about this either. So basically, that's what we are going to use to compare these two models, the Bayes factor. So where does this come from? Probability of D given H1 over probability of D of data given H0. Well, we have it here. This is the probability of the data in H1, and this one is the probability of the data given H0. And when we get that, that's Bayes factor of the alternative over the null. We can do the opposite. Probability of D given H0 over probability of D over H1, and this is the Bayes factor 0,1. We can also calculate Bayes factor 0,1 by doing 1 over Bayes factor 1,0.